Hello and welcome. Today we're diving into the fascinating world of counting principles. This is a fundamental topic in mathematics that helps us solve problems where we need to figure out the number of possible outcomes or arrangements. By the end of this video, you will be able to break down complex counting problems into simpler parts, use the product and addition principles to combine these parts, and apply these strategies to solve a variety of problems. Let's start with a classic introductory problem to see the power of these principles. Imagine a computer can print a line containing all 26 letters of the alphabet in 0.01 seconds. How long would it take to print all possible permutations of the alphabet? At first glance, this might seem impossible to calculate, but by the end of this video, you'll have the tools to solve it. This problem highlights why we need clever strategies for counting, especially when the numbers get very large. To tackle these larger problems, we need to start with the basics. We'll begin with two fundamental rules, the product principle and the addition principle. These two principles are the building blocks for almost all counting problems. Let's illustrate them with a simple example. Imagine you're at a restaurant. The menu has three main courses: pizza, hamburger, and paella. For dessert, you have two options, ice cream and fruit salad. First, let's consider Anna. She wants to order a main course and a dessert. How many different choices can she make? For each of her three main course choices, she has two dessert choices. So she can have pizza and ice cream, pizza and fruit salad, hamburger and ice cream, and so on. The total number of choices is the product of the number of options for each part. That's 3 times 2, which equals 6. This is the product principle in action. Now, let's consider Bob. He wants to order either a main course or a dessert. How many different orders can he make? Bob is choosing from the entire list of items. He can pick any of the 3 main courses, or any of the 2 desserts. He's not combining them. The total number of choices is the sum of the number of options for each part. That's 3 plus 2, which equals 5. This is the addition principle. So to recap, use the product principle when you have to make multiple choices, one after another. Use the addition principle when you have mutually exclusive choices, meaning you can pick one or the other, but not both. Let's formalize these ideas. We'll use the notation NA to represent the number of ways to make a choice A. The product principle, or the AND rule, states that the number of ways to make both choice A and choice B is the product of their individual options. So NA and B equals NA times NB. The addition principle, or the OR rule, states that the number of ways to make either choice A or choice B is the sum of their individual options. This is NAORB equals NA plus NB. A crucial restriction for the addition principle is that the choices must be mutually exclusive. This means there could be no overlap between the options for A and B. For example, you can't use it to count the number of ways to get an odd number or a prime number on a die, because the number 3 and 5 are both odd and prime. The hardest part of applying these principles is often breaking the problem down and deciding which one to use. A good strategy is to rewrite the question to emphasize the AND or OR conditions. Let's look at a worked example. An exam has 10 questions in section A and 4 questions in section B. Part A asks, how many ways are there to choose one question from each section? The key word here is each, which implies and. We need to choose from section A and from section B. So we apply the product principle. The number of ways is 10 times 4, which equals 40. There are 40 different pairs of questions you can choose. Part B asks, how many ways are there to choose a question from either section A or section B? The key word is either, or. We need to choose from section A or from section B. Here, we apply the addition principle. The number of ways is 10 plus 4, which equals 14. You have 14 total questions to pick from. Now let's consider a slightly different type of problem, where we can make the same choice multiple times. This leads us to a general idea. In a class, there are awards for Best Mathematician, Best Sportsman, and Nicest Person. Students can receive more than one award. If there are 12 people in the class, how many ways can the awards be distributed? Let's break this down using the product principle. We have 3 decisions to make. First, we choose one of the 12 people for the Best Mathematician Award. That's 12 ways. Next, we choose one of the 12 people for the Best Sportsman Award. Since students can receive more than one award, the same person can be chosen again. So there are still 12 ways. Finally, we choose one of the 12 people for the Nicest Person Award. Again, there are 12 ways. Using the product principle, we multiply the number of ways for each choice. 12 times 12 times 12, which is 12 cubed, or 1728. There are 1728 different ways to distribute the awards. This leads us to a general rule. Key point 1.3 states that the number of ways of selecting something, r, times from n objects, with repetition allowed, is n to the power of r. In our example, n was 12 and r was 3, so the answer was 12 cubed. Now let's move on to a very important concept in counting, arrangements, also known as permutations. In these problems, the order of the objects matters. Consider the letters in the word arts. If we rearrange them, we can get words like star or rats. Each of these is a different arrangement or permutation of the same 4 letters. How many different permutations are there for these 4 letters? Let's use the product principle. For the first position, we have 4 choices. Once we've placed the letter, we only have 3 choices left for the second position, then 2 choices for the third, and finally only 1 choice for the last position. Multiplying these together, we get 4 times 3 times 2 times 1, which equals 24. There are 24 different ways to arrange the letters arts. This product of consecutive integers is so common in counting that it has its own special notation. It's called the factorial function, and it's written as n with an exclamation mark. N factorial is the product of all positive integers from n down to 1. So 4 factorial is 4 times 3 times 2 times 1. Therefore, the number of ways to arrange n distinct objects is simply n factorial. Let's apply this to a worked example. A test has 12 questions. How many different arrangements of the questions are possible? Since we are arranging 12 distinct questions, the number of permutations is 12 factorial. This is a very large number, 479,001,600. Factorials grow incredibly fast. In examination questions, you'll often need to combine the idea of permutations with the product and addition principles, especially when there are constraints. Let's look at an example. A 7-digit number is formed using each of the digits 1 through 7 exactly once. How many such numbers are even? The constraint here is that the number must be even. This means the last digit must be an even number. It's often easiest to deal with constraints first. The even digits available are 2, 4, and 6, so we have 3 choices for the last digit. Once we've chosen the last digit, we have 6 digits remaining. These 6 digits can be arranged in any order in the first 6 positions. The number of ways to arrange these 6 remaining digits is 6 factorial, which is 720. Now, we apply the product principle. We need to choose the last digit and arrange the remaining digits. So, we multiply the number of ways for each step. 3 times 720, which gives us 2,160. There are 2,160 even numbers that can be formed. Let's try another one. How many permutations of the word square start with 3 vowels? First, let's identify the vowels and consonants in square. The vowels are U, A, E, and the consonants are S, Q, R. The constraint is that the first 3 letters must be vowels. We have 3 vowels to arrange in the first 3 positions. The number of ways to arrange the 3 vowels is 3 factorial, which is 6. The remaining 3 letters are the consonants S, Q, R. These must be arranged in the last 3 positions. The number of ways to arrange the 3 consonants is also 3 factorial, which is 6. Using the product principle, we multiply the number of ways for each part. 3 factorial times 3 factorial, which is 6 times 6, giving us 36. There are 36 such permutations. As we've seen, factorials can get very large. To solve more complicated problems, we often need to simplify expressions involving factorials. This is called the algebra of factorials. The key idea is to use the definition of a factorial to expand the larger one until it contains the smaller one. For example, 9 factorial is 9 times 8 times 7 times 6 factorial. Let's look at a worked example. First, evaluate 9 factorial divided by 6 factorial. We can write 9 factorial as 9 times 8 times 7 times 6 factorial. Now, we have 6 factorial in both the numerator and the denominator, so they cancel out. We are left with 9 times 8 times 7, which is 504. Next, let's simplify n factorial divided by n minus 3 factorial. We expand n factorial. N times n minus 1 times n minus 2 times n minus 3 factorial. The n minus 3 factorials cancel, leaving us with n times n minus 1 times n minus 2. Finally, let's write 10 times 11 times 12 as a ratio of 2 factorials. This is the reverse process. We want to complete the product to form a factorial. We can multiply the expression by 9 factorial over 9 factorial. The numerator becomes 12 factorial, and the denominator is 9 factorial. So the expression is 12 factorial divided by 9 factorial. We can also use this algebraic property to simplify expressions involving sums or differences of factorials. The key is to find a common factorial factor. First, let's simplify 9 factorial minus 7 factorial. The common factor here is 7 factorial. We can rewrite 9 factorial as 9 times 8 times 7 factorial. Now we have 9 times 8 times 7 factorial minus 7 factorial. We can factor out 7 factorial, leaving us with 72 minus 1 inside the brackets. This simplifies to 71 times 7 factorial. Now for a more complex one. Simplify n plus 1 factorial minus n factorial plus n minus 1 factorial. The smallest factorial here is n minus 1 factorial. We will rewrite the other two terms in terms of n minus 1 factorial. N factorial is n times n minus 1 factorial. And n plus 1 factorial is n plus 1 times n factorial, which is n plus 1 times n minus 1 factorial. Substituting these back into the expression, we can now factor out n minus 1 factorial. Inside the brackets, we have n squared plus n minus n plus 1. The n's cancel, leaving us with n minus 1 factorial times n squared plus 1. This technique is very useful for solving equations involving factorials. Let's solve n factorial divided by n minus 2 factorial equals 20. We expand n factorial to n times n minus 1 times n minus 2 factorial. The n minus 2 factorials cancel, leaving us with n times n minus 1 equals 20. This is a quadratic equation. We can solve it by expanding and rearranging. N squared minus n minus 20 equals 0. Factoring this gives n minus 5 times n plus 4 equals 0. The solutions are n equals 5 or n equals negative 4. However, n must be a positive integer for factorials to be defined in this context. So the only valid solution is n equals 5. So far, we've focused on permutations, where order matters. Now, let's shift our attention to situations where order does not matter. This is called a combination. Suppose 3 pupils are to be selected from a class of 11 to attend a meeting. The order in which they are chosen doesn't matter. Selecting Ali, Bill, and Kathy is the same as selecting Bill, Kathy, and Ali. This is a combination. The formula for the number of ways of choosing R objects from n, where order doesn't matter, is given by the symbol NCR, or n choose R. The formula is n factorial divided by r factorial times n minus r factorial. Let's understand why this formula works. First, let's think about how many ways we could select and arrange 3 pupils from 11. This is a permutation 11p3. 11p3 is 11 times 10 times 9, which is 990. This counts every possible ordered group of 3. But for any given group of 3 pupils, say Ali, Bill, and Kathy, there are 3 factorial, or 6 ways to arrange them. Since order doesn't matter for a combination, we've counted each unique group 6 times. To find the number of combinations, we must divide the number of permutations by the number of ways to arrange the chosen objects. So 11c3 is 11p3 divided by 3 factorial, which is 990 divided by 6, giving us 165. This is exactly what the formula does. The numerator, n factorial, is the total number of permutations of all n objects. The denominator, r factorial, divides out the arrangements of the r chosen objects, and n minus r factorial divides out the arrangements of the n minus r objects that were not chosen. Let's work through an example that combines combinations with the addition and product principles. A group of 12 friends wants to form a 5-a-side football team. Part A asks for the number of ways to choose a team of 5. Since the order of players in a team doesn't matter, this is a combination. We need to choose 5 players from 12. Using the formula, 12 choose 5 is 12 factorial divided by 5 factorial times 7 factorial, which calculates to 792. Now for part B, Rob and Amir are the only goalkeepers and cannot play in any other position. The team of 5 must contain exactly one goalkeeper. How many ways can the team be chosen? This problem has a constraint, so we should break it into cases. The team must have exactly one goalkeeper, and there are 2 possible goalkeepers, Rob or Amir. These are mutually exclusive cases, so we'll use the addition principle. Case 1. Amir is the goalkeeper. There's only one way to choose Amir. We still need to choose 4 more players for the team. Since Amir is chosen and Rob cannot play in any other position, there are 10 remaining players to choose from. So we choose 4 from 10, which is 10c4, or 210 ways. Case 2. Rob is the goalkeeper. Similarly, there's one way to choose Rob. We again need to choose 4 more players from the remaining 10. This is also 10c4, or 210 ways. Finally, we add the results from our 2 mutually exclusive cases. The total number of ways to choose the team is 210 plus 210, which equals 420. Sometimes, it's easier to count what you don't want and subtract it from the total. This is the exclusion principle. The principle is simple. To find the number of ways that do not have a certain property, you find the total number of ways and subtract the number of ways that do have that property. Let's revisit a problem from earlier. How many 5-digit codes formed using the digits 1 through 5 exactly once do not end in 25? We want to find the number of codes that do not end in 25. Let's use the exclusion principle. First, we find the total number of possible codes. This is the number of permutations of 5 distinct digits, which is 5 factorial, or 120. Next, we find the number of codes that do end in 25. We treat 25 as a single block. The remaining 3 digits, 1, 3, 4, can be arranged in 3 factorial, or 6 ways, so there are 6 codes that end in 25. Finally, we subtract. The number of codes that do not end in 25 is the total number of codes minus the number of codes that do end in 25. That's 120 minus 6, which equals 114. The exclusion principle is especially useful for problems with at least or at most conditions. Theo has 8 jigsaws and 5 toy bears. He chooses 4 things to play with. In how many ways can he make a selection with at least 2 bears? At least 2 bears means he can choose 2 bears, 3 bears, 4 bears, or 5 bears. This would involve calculating 4 separate cases and adding them up. It's much easier to use the exclusion principle. The opposite of at least 2 bears is fewer than 2 bears, which means 0 bears or 1 bear. We'll find the total number of ways to choose 4 items and subtract the ways with 0 bears and the ways with 1 bear. First, the total number of ways to choose 4 items from the 13 available is 13c4, which is 715. Next, the number of ways to choose 0 bears and 4 jigsaws is 5c0 times 8c4, which is 1 times 70 or 70. The number of ways to choose 1 bear and 3 jigsaws is 5c1 times 8c3, which is 5 times 56 or 280. Finally, we subtract. The number of ways with at least 2 bears is 715 minus the sum of 70 and 280. This gives us 715 minus 350, which is 365. Let's return to permutations, but this time we'll look at a more general formula for counting ordered selections. Sometimes we want to choose a number of objects from a bigger group and arrange them. For example, finding the possibilities for the first 3 finishers in a race. Consider a class of 28 pupils. They need to select a committee with 4 specific roles: a class representative, a treasurer, a secretary, and a football captain. Each post must be a different person. How many different ways can the 4 posts be filled? This is a permutation because the order matters. Being the representative is different from being the treasurer. We are choosing 4 people from 28 and arranging them into 4 positions. We can think of this as a 2-step process. First, choose the 4 people from the 28. This is a combination. 28 choose 4. Then, arrange those 4 people into the 4 roles. This is a permutation of 4 objects, or 4 factorial. Using the product principle, we multiply these 2 steps. The number of ways is 28 choose 4 times 4 factorial. This calculates to 491, 400. This leads us to a general formula for permutations. The number of permutations of R objects, chosen from N, is denoted NPR. It's calculated as N factorial divided by N minus R factorial. This is equivalent to N times N minus 1, down to N minus R plus 1. Let's see how this formula relates to our 2-step process. Remember, NCR is N divided by R in R. If we multiply this by R, the R in the denominator cancels out, leaving us with N divided by NR, which is exactly NPR. So NPR is just a shortcut for choosing R objects and then arranging them. Let's tackle a common type of permutation problem, arranging objects with constraints, specifically when some objects must be kept together. How many permutations of the word square have the Q and U next to each other? The constraint is that Q and U must be together. The trick here is to treat the group of objects that must stay together as a single, larger object. Imagine the letters of square on tiles. If Q and U must be together, we can glue them together to form a single QU tile. Now, instead of 6 individual letters, we are arranging 5 objects, S, Q, U, A, R, E. The number of ways to arrange these 5 objects is 5 factorial, which is 120. However, we must also consider the arrangement within the QU block itself. The letters Q and U can be arranged in 2 ways, QU or UQ. The number of ways to arrange Q and U is 2 factorial, which is 2. Using the product principle, we multiply the number of ways to arrange the blocks by the number of ways to arrange the letters within the block. So, 5 factorial times 2 factorial, which is 120 times 2, giving us 240. There are 240 such permutations. This leads to our key point. If a group of items must be kept together, treat them as one object. Then, remember to multiply by the number of permutations of the items within that group. Now, let's look at the opposite constraint, when objects must be kept apart. This requires a different strategy. How many permutations of the word square have none of the vowels together? The vowels are U, A, E. The consonants are S, Q, R. The trick here is to first arrange the objects that are not restricted and then place the restricted objects into the gaps created. First, arrange the 3 consonants. This can be done in 3 factorial, or 6 ways. Let's consider one such arrangement, SQR. Arranging the consonants creates gaps where the vowels can be placed so that no 2 are next to each other. For the arrangement SQR, there are 4 possible gaps: before S, between S and Q, between Q and R, and after R. We need to place our 3 vowels into 3 of these 4 gaps. First, we choose which 3 of the 4 gaps to use. This is a combination, 4 choose 3, which is 4 ways. Once we've chosen the 3 gaps, we need to arrange the 3 vowels U, A, E into those gaps. This is a permutation, 3 factorial, which is 6 ways. Finally, we multiply the results from our 3 steps. The total number of permutations is 3 factorial times 4. Choose 3 times 3 factorial, which is 6 times 4 times 6, giving us 144. The key point for keeping objects apart is to first permute the other objects, and then count the permutations of the gaps created. Let's revisit our introductory problem now that we have all the necessary tools. The problem was, If a computer can print a line of 26 letters in 0.01 seconds, how long would it take to print all possible permutations of the alphabet? First, we need to find the total number of possible permutations of the 26 letters of the alphabet. Since we are arranging 26 distinct letters, the number of permutations is 26 factorial. This is a massive number. Let's use a calculator to find its approximate value. 26 factorial is approximately 4.03 times 10 to the power of 26. That's a 4 followed by 26 digits. Now, we need to calculate the total time. The computer prints one line in 0.01 seconds. So the total time is the number of permutations multiplied by the time per line. This gives us approximately 4.03 times 10 to the power of 24 seconds. This number is so large, it's hard to comprehend. Let's convert it to years to get a better sense of scale. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. Dividing our total time by this product gives us approximately 1.28 times 10 to the power of 17 years. To put this in perspective, the age of the universe is estimated to be about 14 billion years, or 1.4 times 10 to the power of 10 years. Our calculated time is approximately 10 million times longer than the universe has existed. This demonstrates the incredible power of counting principles and how quickly the numbers can grow. Let's quickly summarize the key concepts we've covered today. We started with the product principle, or the AND rule, which tells us to multiply the number of options when we make multiple choices. We then learned the addition principle, or the OR rule, which tells us to add the number of options for mutually exclusive choices. We introduced the factorial function, n factorial, which is the product of integers from n down to 1. This is used to count permutations, where order matters. The number of permutations of R objects from n is NPR. We also learned about combinations, where order does not matter. The number of combinations of R objects from n is NCR, calculated as n factorial divided by R factorial times n minus R factorial. Finally, we explored two powerful strategies for dealing with constraints: the exclusion principle, where we subtract unwanted cases from the total, and the methods for keeping objects together or apart. You are now equipped to break down complex counting problems, apply the correct principles, and solve them systematically. Practice is key to mastering these techniques. To help you solidify your understanding, here are 5 practice questions. Take your time to work through them, applying the principles we've discussed today. Question 1. A committee of 5 people is to be selected from a group of 12 boys and 8 girls. How many different committees can be formed if it must contain exactly 3 boys and 2 girls? Question 2. In how many ways can the letters of the word triangle be arranged if the vowels A, I, E must always be together? Question 3. A password consists of 4 different letters from the English alphabet, followed by 3 different digits from 0 to 9. How many different passwords are possible? Question 4. A group of 10 friends are going to the cinema. There are 10 seats in a row. In how many ways can they be seated if 2 specific friends, John and Mary, must not sit next to each other? Question 5. Solve the equation NP2 equals 72. Thank you for watching. Keep practicing, and you'll become a master of counting principles.